So today we have a cool geometrical problem. We take a circle. Now we draw two chords so that they meet each other at 90 degrees. Now we can see that as the chords are intersecting, they are getting divided into line segments. Now taking each of this line segment as the diameter, if I draw 4 semicircles like this way, the question over here is what fraction is shaded. In simple words, you have to find the value of the fraction, the total blue area upon area of the circle. So this is Anmol, and now let us see the solution. How can we solve this problem? Okay, now let us start with the solution. So the first thing that I will do is I will mark the diameter of all these 4 semicircles as variable. So let the diameter of this first semicircle be equals to A, the diameter of the second semicircle be equals to B, the diameter of the third semicircle be equals to C, and the diameter of the fourth semicircle be equals to a variable D. Okay. Now as we have taken the diameter of this semicircle as variable, we can easily write down their areas. So we can say that the diameter of the first semicircle is equals to A. Therefore the area of the first semicircle becomes pi times A upon 2 the complete square divided by 2. Area of a semicircle is pi by 2 into the radius square. Now similarly the area of the second semicircle would be pi into B upon 2 the complete square divided by 2. The area of the third semicircle would be pi into C upon 2 the complete square divided by 2. And finally the area of the fourth semicircle would be pi into D upon 2 the complete square divided by 2. Okay. Now the question over here was to find the value of the fraction total blue area upon area of the circle. So ultimately if I will add these 4 areas, it will give me the total blue shaded region divided by area of the circle. Now we can see that we have neither marked the diameter or the radius of this circle. So let us do that. Now this thing is obviously clear that this point is not the center, so we have to take it somewhere over here. So let this point be the center of the circle and the radius of this circle be equals to a variable capital R. Okay. Now if the radius of the circle is equals to capital R, area of the circle becomes pi times the radius square. Okay. Now I can see that the pi from the numerator and from the denominator can be easily factored out. And now if I will open the square brackets and do some simplification, the final result will look like A square plus B square plus C square plus D square divided by 8 times the radius square. So ultimately the value of the required fraction has now turned out to be this particular thing. Now let me ask you a question. Is this answer correct? So the answer is no. Why? Because in such type of question in which we have to find the value of such kind of fractions, usually if in the question we have any kind of variable, this fraction has to be found in terms of that particular variable. And if in the question we have not given any kind of variable already marked, this means the value of this fraction is some kind of real number. Okay. And also we cannot give the answer to a question in terms of the variable that we have put from our side. So this answer is not correct. We need to even simplify this thing further. And as I have told you, in this question we were not having any kind of variable already given. This means the value of this particular fraction has to be a real number. Now in order to get the value of this particular fraction as a real number, we need to get a relation between the complete numerator and the complete denominator. Okay, now we have to try to find a relation between the numerator and the denominator. And for that, we will use the arrangement of this particular diagram. Look carefully, till now what we did is just a simple marking of the diameter of the semicircle, the addition, and that gave us this particular fraction. But what we have not utilized till now is that these are straight chords and they are meeting each other at 90 degrees. This is the fact that specifies the arrangement of this diagram. So for that I will draw the complete circle over here, and inside this I have to draw two chords that are meeting each other at 90 degrees. It is the same diagram, I have just removed the semicircles. Okay. Now the length of this chord we have already taken in the first diagram, that are going to be A, B, C and D. Okay. Now what I can observe is that the complete length of this particular horizontal chord is going to be A plus C, and the complete length of this vertical chord is going to be B plus D. Okay. Now as we have discussed, the center of the circle is not this particular point, it has to be somewhere over here. Okay, so here we have marked all the basic things. Now we will proceed to a thing that is ultimately a theorem. A theorem telling us a relation between the radius of the circle and the chords that are going to be intersecting at 90 degrees inside the circle. Okay. So the first thing that I will do is I will drop a perpendicular from the center of the circle to this horizontal chord. Now we know this particular fact that when we draw a perpendicular from the center of this circle to the chord, it will bisect the chord, and the theorem is very easy to be proved. We simply draw the radius to the endpoints of the chord. Radius equal, common side equal, and here is the 90 degree. These both triangles become congruent to each other because of right angle hypotenuse side, and as triangles are congruent, rest of the things between them become equal, and from there we get this length equals to this length. Okay. Now the complete length of this horizontal chord was equals to a plus c. Now because of this point where the 90 degree is meeting the chord has got bisected into equal parts. The complete length of the chord is a plus c, hence the bisected part would have a length a plus c divided by 2. Okay. Now the distance from here to this 90 degree point where the chords are intersecting, the distance is equals to a. And the distance from this particular point to the point where the 90 degree is meeting the chord, the distance is going to be again a plus c upon 2. Okay. Now the bigger distance is a plus c upon 2. The smaller distance is equals to a. Therefore the remaining distance, that is of this particular line segment, would be equals to a plus c upon 2 minus a, and this will give us an output is c minus a divided by 2. Okay. Therefore the distance of this particular red line segment inside this diagram is going to be c minus a upon 2. Remember that. Okay. Now I will just remove this particular thing and draw one more perpendicular, and this time it will be from the center of the circle to this vertical chord. Okay. Now the same thing, we drop a perpendicular from the center of the circle to a chord, it will bisect the chord. The complete length of this chord is b plus d. Now because of this point where the perpendicular is meeting the chord, the distance will get bisected, and the length of the resulting output would be b plus d divided by 2. This is the length of this line segment. Okay. Now I can say one more thing over here. Okay, now it's looking more beautiful and it will be easy to be explained. Now I can say that the chords were meeting at 90 degree, therefore the angle formed over there would also be 90 degree by linear pair. Now inside this quadrilateral, by angle sum property, this angle would be 90 degree. A quadrilateral, all the four angles are 90 degree, hence it is a rectangle. In rectangle, opposite sides are equal. Now recall that we have got the length of this particular line segment, and that was equals to c minus a upon 2. Therefore the length of this line segment is c minus a upon 2, hence the length of this line segment also becomes c minus a upon 2. Now what I will do is I will simply draw the radius of this particular circle, and the radius is simply a line segment from the center to the boundary, hence this blue lines become the radius, and I will take it as a variable r. Okay. Now we can say that here we have this right angle triangle. So if I apply the Pythagoras theorem, we will get b plus d upon 2 the complete square plus c minus a upon 2 the complete square equals to r square. Okay, so we have got this particular equation over here, and you might be thinking that yes, we have got the equation in which we needed a relation between the a, b, c and d and r. Yes, you are correct, but what if I tell you that this thing can even be simplified, and that will make this equation even look more beautiful? What if I tell you that the negative 2ac and the positive 2bd can be cancelled out? Isn't that interesting? But the question arrives, how they got cancelled out? So for that we need to just look back to the diagram and redraw it. Now the theorem that we are going to just discuss is known as the intersecting chord theorem. The name itself says that inside a circle, when two chords are intersecting, we can apply this theorem. And in this theorem, there is no requirement of the data at which angle the chords are intersecting. Here in our particular question, the chords are intersecting at 90 degree. I'll just not take as 90. I will take that thing as anything like a variable theta. Now we are going to discuss the general case. Okay. Now what I will do is I will take the length of this particular chords as P, Q, R and S. Okay. Now I will draw three line segments like this way. Now we know this particular theorem. From the same chord, if there are two angles subtended in the circle, they both are equal to each other. Hence this angle and this angle become equal, and let it be equals to a variable alpha. This angle is equals to theta, therefore by vertically opposite angle, this angle over here is also equals to theta. Now what I can observe is that this triangle and this triangle are similar to each other because two of the angles of this triangle are equal. So once two triangles are similar, the ratio of their sides become equal. So according to the correspondence, the ratio of the side will look like R upon P equals to Q upon S equals to, let this be M and this one be equals to N, therefore M upon N. Now what I will do is I will simply compare these two and do a cross multiplication over there. So I will get R into S equals to P into Q. Now the same theorem we will apply over here. We can see that these two chords were intersecting with each other. Therefore by this intersecting chord theorem, the product of AC would be equals to the product of BD. Okay. Now coming back to this equation. Now as I told you, these two things were going to be cancelled out. And the reason is now clear, as we can see the product of AC is equals to product of BD. So in this we have negative 2AC and positive 2BD. So I can simply replace the value of BD as the value AC. So we can see that negative 2AC positive 2AC got cancelled out. So now the equation will look like A square plus B square plus C square plus D square equals to 4 times R square. And you may notice one more thing. We have got a relation between the numerator and the denominator of the required fraction. Now let us write down the final answer of the solution. So as we have already got the value of the required fraction as this particular thing, we have A square plus B square plus C square plus D square. I will replace that thing as 4 times R square. 4 times R square in the numerator divided by 8 times R square in the denominator that was already present over there. Now R square got cancelled out from the table of 4, it cancelled out as 2. So the final answer is equals to 1 upon 2, and this is the answer that we were looking for. The combined area of 4 semicircles that will arrange like this way would be equals to half the area of the complete circle. So this was my way to solve this particular problem. If you have any other method other than this, do comment below, and if it's hard to comment, you can email me or else you can send it to me on my Instagram. The link is in the description.